on lesson 8.2, still in applications logarithms. This is Newton's law of cooling that we're going to look at today. So Newton's law of cooling states that the difference in the temperatures of a warm body and its cooler surroundings decreases exponentially. That is also the same as something that is going to change and increase exponentially as well. If you look at the formula for this, it is very similar to the formula that we used in 8.1. Only difference is instead of the N and NO, we're using H and HO. And the only change of that is because in this formula, H is going to stand for available heat. Available heat. Not the actual temperature of the object, but available heat. So we'll look at that. Available heat is the difference between the object's temperature and the constant temperature of the environment. That's what available heat is. I highly recommend that you make a table for the problems, or at least organize your information. I'm going to use a table in my examples. It's a real easy thing. There's going to have 4 columns: time, the constant temperature of the environment, the object's temperature, and what you're going to use in the equation is available heat. Alright, so we're going to use the formula above, and we're going to make a table here. Time, constant temp, object temp, and available heat. Suppose you pour a cup of coffee at 100 degrees Celsius in a room with a constant temperature of 20 degrees Celsius. 5 minutes later, the coffee temperature is 90 degrees Celsius. How long must you continue to wait before the coffee cools to your drinking preference of 45 degrees? Well, what is it we know about the constant temperature? Constant temperature of 20. What do we know about the object's temperature? Well, the cup of coffee began at 100 degrees, cooled to 90, but we're looking for a temperature of 45 degrees. From those temperature values, we can find the available heat. It is the difference, as it's defined above, it is the difference between the object's temperature and the constant temperature. So in this case, it's 80, it's 70, and then it is 25. What about times? Well, there is no actual time of day, but we will consider the starting time to be a time of 0. The next temperature recording that we have was 5 minutes later, so we'll call that t equals 5. And then we have a question about how long, so that's referencing to our time, must we wait? That's our unknown. In all of these Newton law of cooling problems, you must first determine the rate. We do not have a rate given to us. For all of them, your rate will be less than 1 because this available heat will always be shrinking as time passes. That's just kind of a common sense idea in the fact that if you think about it, if you have a temperature in a room, if you bring something colder than that temperature in, then that object's going to warm up until it gets to the room temperature. If you bring something warmer, it cools off until it gets to that constant temperature. And so that available heat will always be decreasing as time goes by. But as I mentioned, we're going to first determine the rate. So the rate, I've got to use the 2 occurrences that I have all of the information for, which is at time 0, time 5. So I'm going to have the H, which is the later occurrence of available heat, which is 70 at time 0. Starting time, it was 80. Do not know the rate. What about the times? Well, the time T is the time it took for 80 to become 70, which was 5. And for Newton's law of cooling, not for the ones that we did in 8.1, but for Newton's law of cooling, the time of the rate will be for a minute. For all of Newton's law of cooling, we'll use 1 minute as the K. So remember from 8.1 I mentioned that when you have the ending amount and the starting amount, you should always begin by dividing. So we're going to divide both sides by 80, which gives me 7/8 is equal to b to the 5th. If you will think back to the last unit, how are we going to get b by itself when it's raised to a power of 5? We're going to use that reciprocal exponent, which means raising it to the 1/5 power, which simply is the 5th root of 7/8. And so we'll get our calculator out and we will take in parentheses 7 divided by 8 and raise that, and I'm going to put my exponent in parentheses because it's a fraction. 1 divided by 5. So my rate of change is 0.9736. We will use 4 decimal places for accuracy purposes. I will be looking in your assessments for 4 decimal places unless it rounds to 3. So our rate of decrease is 0.9736. It's actually decreasing at nearly 3% per minute. Okay, now we're going to go back and actually answer the question at hand, which is at what time or how long must we wait until the coffee cools to the drinking preference of 45 degrees. So my ending value of available heat will be 25. You'll have the choice to use either of those other available heats, but you'll just keep in mind that your answer will be in relation to whichever one of those that you chose. So I'm going to use the 70. I'm going to take my rate of 0.9736 and I'm looking for the time that it's going to take for it to become 25 degrees available heat or 45 degree object temperature, coffee temperature. And our K again is 1. So if you don't write that, that will be okay. What's my first step? Yes, I will divide first because I've got both of these temperatures. So I'll divide by 70. 25 over 70 is equal to 0.9736 to the T. Again, going back to our last lesson in 8.1, anytime you're looking for the exponent, we're going to be using logarithms to do that. And so this number that's being raised to the power is our base. So we've got a log, base of 0.9, glad I'm using pencil this time, 0.9736 of 25/70ths is equal to our time. We'll use that change of base, let me clear that, which means it's the log, 25 divided by 70, close parentheses, divided by the log of the base. You always divide by the log of the base, which is 0.9736. That's going to give me my time, which is 38.5. What is the unit for my time? We'll go back to what I said was the unit that we'll always use for our K, and that was minutes, and so we've got 38.5 minutes. So it's going to take you a little over a half an hour before your coffee sitting in that temperature will actually cool to the temperature you prefer to drink. Okay, let's move on to the next example. Precisely 3:48 p.m., our hero, Inspector Bentley, discovers a murder victim in an abandoned warehouse in which the temperature is 21 degrees. The inspector immediately determines that the body temperature of the victim is 31 degrees. 1 hour later, the body temperature is 29 degrees. We are assuming the body temperature at death to be 37 degrees Celsius, which is 98.6 degrees Fahrenheit. Determine the time of death. Okay, we will set up our table. So 3:48 p.m. is the time. What's the constant temperature? 21 degrees. What about object temperature? Well, at 3:48 is when your hero, me, discovered the victim. At that time, the body temperature was 31. 1 hour later, which would be 4:48 p.m., the body temperature was 29. What we do not know is the time of death. What we do know, or as it said, we're assuming that it was 37 degrees, which was the normal body temperature. Okay, let's determine our available heats. At 3:48, that would be 10. At 4:48, that would be 8. And at the time of death, that would be a difference of 16 degrees. Okay, so we go back to what I said in the first example. You have to look for 2 complete rows of information. We'll set up, and what's the first thing that we're going to look for? Correct, the rate. So we'll start with the later time, available heat, which is 8, equal to 10. Something to keep in mind, as I mentioned earlier, the available heat will always be decreasing, so the number on the left will always be smaller than the available heat on the right. If you have those larger on the left, you have made a mistake. Always smaller on the left. We do not know the rate, the B. What about time? How much time did that take to elapse for 10 to become 8? Well, it took an hour. You will not use 1 hour. We're always going to have our B in minutes, and so I'm going to need to turn that 1 hour into 60 minutes. Let's solve, which requires us dividing by 10. Dividing both sides by 10 is 8 over 10, which is 0.8. 8/10 equals B to the 60th. We need to get rid of our exponent of 60, which means we raise it to the 1/60th power. Use our calculator. Whoops, clear it out. We'll take 0.8 and raise that, and I'll put in parentheses my exponent, since it's a fraction, 1 divided by 60. I get a rate of 0.996, and we'll round to 3. The 8 rounds it to a 3. That's our rate. Now we'll go back and solve and find out time of death. Taking our rate, and as I mentioned, you can use either one of those times. Sometimes you'll have maybe a time of noon. That's usually an easier time to use. These are both basically the same, so I'm not sure that one's going to be easier than the other. I'll just go ahead and use the 10. If you'll notice, this actually occurred sooner instead of after the fact, and so I'm going to have to put the 10 on the left and the 16 on the right, going from what I mentioned earlier, the smaller number always on the left. My rate, 0.9963. I'm looking for the time, that's my unknown. I know that it's going to be in minutes, and of course it's over 1. We'll divide, 10 divided by 16, 5/8 equals 0.9963 to the t. Again, solving for an exponent, which just happened to be that both of these were solving for an exponent. You might not be solving for an exponent. We'll look at that later. This becomes the log of 5/8 divided by the log of the base, which is 0.9963, is equal to our time. Move it over here. Log, oops, 5 divided by 8 divided by log of 0.9963. Enter. I've got 126.8 minutes. How about take out that extra 6 there for some reason I wrote. Now, I can't just use that in terms of minutes because this problem actually references time of day. So what I'm going to need to do is convert this into amount of hours in minutes. What I can do is round this to the nearest minute, which would be 127 minutes. 60 minutes in an hour, and so that would be 2 hours 7 minutes. That 2 hours and 7 minutes occurred before the time of 3:48. If I had used the 8 in the problem instead of the 10, I would have gotten a larger number here, but I would have been working off of a 4:48 time. Since I used the 10, we're going to work off of a 3:48 time. So I'm going to go back in time 2 hours and 7 minutes from 3:48 p.m. So if I go back 2 hours, I'm at 1:48. I've got to go back 7 more minutes, so that becomes 1:41 p.m., the approximate time of death.